we have Norm Cooper, another sort of change of pace. Norm Cooper received his BSc with a major in Geophysics.
Oh, sorry, keep going. Just wondering which presentation. Okay.
Major in Geophysics from UBC I've lost my place here, in 1977. After a short experience at the mining industry, he joined Amoco Canada, the petroleum company. With Amoco, he was allowed to free hand in experimenting with unique field and processing methods. This practical experience, combined with Amoco's training program, armed Norm with solid geophysical tools. Prior to leaving Amoco, he became involved at their training centre in Tulsa, Oklahoma, periodically teaching courses as part of their geophysical training program. In 1981, Norm moved to Voyager Petroleum. There he became directly involved with seismic field operations and program design, in addition to his normal interpretation and exploration responsibilities. His field experience was broadened to encompass all of Western Canada, as well as minor exposure to the Beaufort, East Coast and Northern States. By late 1983, Norm felt the urge for independence and founded Mustagh Resources. Since then, he's been very active in geophysical consulting, survey design and general exploration. He's developed a series of courses focusing on fundamental seismic principles and acquisition and program design. Teaching now constitutes about 40% of Mustagh's business. Norm and his partner, Yajaira, have presented a broad variety of courses to thousands of geophysicists and contractors around the world. Welcome, Norm.
Thanks, Brendan. You obviously didn't get my short biography, but you know. Okay. I had to highlight seismic in here. I didn't have seismic in my original title. When I saw all of the other titles of today's papers, I realized there was a lot of 3D. I better make sure that you understand this is about seismic. I'm grateful to Craig in that last presentation. He actually mentioned the word P wave velocity. I think it's the first technical term I've understood all day. So this is about seismic. It's a tool primarily used in the oil and gas business, and it's being used more and more often in the mining business. We've had the pleasure of working with Brendan on a couple of different mining projects, carbon gold deposits, recently some coal. We've worked in Mongolia and another foreign country called Saskatchewan. We've worked in uranium exploration, coal bed methane in Australia. So it is becoming a little more popular. It's a little more costly tool than most mining people are accustomed to. And we'll see why as we go through this presentation. Okay, 3D seismic has been around since the mid-80s. It's by far the most common kind of seismic done these days. And our focus, our specialty, Yajaira and myself, is to design seismic programs effectively for our clients' purposes, which usually means making sure we can image what they need to see without spending too much money, which is pretty much everybody's objective. Okay, a lot of designers focus on imaging signal. Okay, so what do we mean by signal? Here's a model cross-section through a very simple geologic setting, a buried focus channel. And hopefully this will work, or it might not. That's funny, it worked just a little while ago. My animations, no, that's wonderful too. Here we go. No, just my luck. I've got about 5 animations in here, and I get you none of them are going to work, I guess. This is supposed to show a propagating wave field, a pressure wave, a P wave field moving through the earth, and what we're trying to measure is reflections from that wave field. So measuring signal is normally about measuring reflections and diffractions, things coming from geologic events in the subsurface. Okay? If you'd seen the wave equation model, you might understand what this is. This is a seismic shot record. Again, it's showing the reflections from shallower and deeper horizons. It's showing diffractions. These are what we consider to be signal. What most people don't focus on are various modes of noise, the undesirable things that we record and we need to separate when we process our data. So I'll just run through some of the different types of noise that we have. The signals are things we generally understand. We have a good geologic model. We can predict what the reflection seismic signals might look like. The various sources of noise we may or may not understand. Okay? So some of the simple ones, there's surface waves, direct waves, as shown in the blue here. These are shear waves. They're the same travel path as the blue wave, but it's traveling as a shear wave rather than a P wave. You will see in here as well more shear waves on this side of the shot record, some ground roll, rally waves in here. These are all high amplitude surface waves. They haven't traveled a long ways through the earth. They're not reflecting back. They remain very high amplitude, much higher amplitude than the reflection signals we're trying to measure. Those are coherent noise modes. Just more examples here of ground roll and shear waves, and very little evidence of typical reflections. So what kind of things might be causing noise that just masks all our reflections? Here I've got a very simple model showing a near-surface low-velocity layer overlying a bedrock surface. These layers can create standing waves, or tuned waves, guided waves, whatever you want to call them. They're just nasty crap that makes it difficult for us to see our reflections in our seismic records. So these are reverberations of surface waves. You'll see tuned waves. There's a fundamental frequency in here, and you can even see the harmonics in between there. So guided waves, that's a type of noise. Again, it's a coherent kind of noise, trackable from trace to trace. This one is showing backscattered noise. So we're seeing a refraction up in here, we're seeing a direct wave coming down here, and we're seeing the surface waves being propagated backwards towards our energy source. So there's all kinds of backscattered noise. Notice in this record, on one side, we get a relatively good seismic record where we can see reflections from deep geology. On this side, the surface waves dominate. They're much stronger than our reflection amplitudes, and they inhibit us from mapping the geology. Okay? Again, we have on the left side reflections. That's what we would like to see. That's what most of us model and design for. On the right side, these are two simple scattering points. Those are actually near-surface scattering points where the sound has traveled out of the plane of the 2D seismic section, encountered some inhomogeneity, and is now scattering back across our receivers. Again, high amplitude and obliterating our ability to see reflectors. And if you get a lot of those chaotically scattered waves, they can look like this area in here. So quite often we'll see records that they'll have the direct wave, they'll have the refraction, they might have reverberations, all of which looks pretty nasty. Those are all coherent events which we can manage in processing. What we have in here is chaotically scattered versions of those surface waves. They're not coherent, they're difficult to process out. Okay? So for example, a little bit of simple filtering will reveal reflections underneath those reverberations. Over in the scattered area, we just really have difficulty pulling out the reflections and useful signal. So estimating under what conditions we're going to have this type of noise and how bad it's going to be, this is not easy your first time into an area. So the title of this paper is all about designing your second seismic program. Okay? We're going to have to use lessons learned from our first pass through an area and use that information to predict how the noise in that area is going to affect our next design. Okay? So let me show you with an Alberta example. This is a 3D seismic program in central Alberta, west central Alberta. 3D seismic program, you can see the scale down here in the bottom right, that's 3 kilometers across the scale. We have a grid of source and receiver lines with a separation between our source lines and a separation between our receiver lines. And those are two key parameters in a 3D seismic design. How tight does that grid need to be? And you're cutting through forests, you're crossing farmers' lands and permitting them. It's easy to understand that a tight grid is going to be an expensive grid. A sparse grid is going to be much more affordable. Okay. All right, from that 3D survey, here's an inline section taken from the 3D processed cube. And we can see some, for our client in this area, this was a key horizon. Okay, so now we're talking about color color standards in interpreting seismic data in Alberta. Yellow means something sandy and Cretaceous and sedimentary. This is one of his key horizons in here, and affecting his key horizons is some of the reverse faulting that you see coming through here. And in case it's been a long time since you've interpreted a seismic line, I've helped out here by highlighting those faults. Whoops. Okay, so the continuity in the shallow beds is also very important to our client in this area. Okay, equations. We've seen enough of those today. I'll keep this one really simple. Basically, this is saying in a 3D design, the product of our source line spacing and our receiver line spacing, that's what we call the box area or your grid density. What is necessary to achieve good imaging is directly related to your geologic objectives. How deep is your target? Okay? So again, the difference between my normal world, the oil and gas world, is we're talking about thousands of meters. In your normal world, you're talking about hundreds of meters normally. Okay? Notice that as the depth diminishes, your line spacings must become smaller and it's going to be more expensive. So one of the reasons why it gets harder to justify 3D seismic in the mining environment. Shallow is expensive. Okay? Our line spacing is proportional to depth of target squared. It's inversely proportional to your geophysical objectives. How much fold do you need to do the attribute analysis that you want to do? So the right side of this equation is what most people use for designing seismic programs, just the minimum we need to image our reflectors. What happens when you introduce some of this scattered noise that I've shown you is that the solution to that is to drive your line spacing smaller and smaller. And so the question will arise, you've shot a program, you've had some degree of success. The next time you shoot a program, do you need to shoot it with a greater density, a smaller line spacings to get better quality? Are you satisfied with the quality? And could you shoot with a larger spacing and save more money? So this is the question we're going to attempt to answer. Your second program in an area, if you're going to make adjustments, do you need to get better data, or can you afford to save some money? How are you going to judge that? Okay. So in this example, the client had shot with a particular line spacing with 420 by 480 meter line spacings on his 3D grid. All right. The question arises the next time he shoots, could he use a sparser grid and still get pretty good results? Or should he go to a tighter grid and spend more money, and would he get significantly better results? And either way, how is he going to convince his manager which way to go? Okay? So we can look at the basic model statistics that everybody uses in designing. We can look at the grid densities. So again, this grid is what the client had used so far. Could he go sparser and save money? Does he need to go tighter and spend more money but get a better image? How is he going to make that decision? We can look at statistics like fold. How many traces are we going to have in each subsurface bin? Fold is a relatively useless statistic. It tells you how much redundancy you're building into your survey, but it doesn't tell you about the quality of the statistical distribution of your traces. Okay? We can look at how completely are we measuring different source-receiver offsets. Basically in these plots, red is good, blue is bad. So again, as you go denser line spacings, you get better looking statistics. But what does that mean? Do you need to spend money? Do you need to get more red in these plots? There's no way of telling. I said fold is not a very useful statistic. So a more useful statistic is the diversity of the traces with which you're imaging the geology. Okay, so we can talk about a bin, one set of midpoints that is imaged by many different traces. So blue sources into red receivers, those are the traces we're recording, and we believe we're imaging something related to the midpoint between those. This is showing 20-some traces that are recorded in a 3D survey, all of whom image the same midpoint, or possibly the same geology. So that'd be a 20-fold trace. Okay? But is it a good set of information, or is it a useless set of information? So what we'll do is we'll take these so-called source receiver offsets and azimuths, and we'll plot them in a polar plot. called a spider. Well, sometimes they call it a spider plot. If we just plot the polar coordinates at the tips of the vectors, we get this guy. So what this is saying for our target, we can probably use source receiver offsets from 0 out to some maximum value. That's the radius of this curve. And for each trace that falls in a subsurface bin, we can map its offset. We can map the source receiver azimuth, the direction of the trace. And what you would like to have is a bin that has lots of samples. That's your fold. Okay? But fold by itself is not an important statistic. You want lots of samples that are diversely measuring different offsets and azimuths. You don't want a lot of samples that make the same observation over and over again. That's not good geophysics in any of our, in any of our disciplines. Okay, so we use these plots that are often now called a common offset vector plot, COV plot. And again, we look at these 5 different models. We can predict the statistics. We can say, here's what you got in your last survey. That's what you would get if you go sparser grid. This is what you'll get if you go a tighter grid. It still doesn't tell the interpreter or the manager, does he need to go one way or the other, and what would he gain or lose. Okay? So the model statistics just aren't sufficient. They don't take into account the variation of signal from one area to another, or the variation in particular of noise. So the tool I want to introduce here is called, we call it data simulation. From an existing data set, an existing 3D, we're going to go to that 3D and we're going to collect what's called a super gather. So this is a detail looking at several bins of a 3D. Each of these might be 20 by 20 or 30 by 30 meter bins. Each bin may be imaged by many different source receiver pairs. Okay? And those source receiver pairs may represent many different offsets. So that's what these little vertical lines mean in each bin. It's how many different traces you have of different offsets. Okay, in any one bin, you may find that there's offsets that are not measured. Okay, and each bin is different than adjacent bins. So what we do is we gather together several adjacent bins that cover what we believe to be a small, an area that's small compared to your rate of geologic change, but large enough that when we combine them, we'll get many traces of representing all different possible statistics, all different source receiver offsets. So that's what a super gather looks like. It's a collection of traces after data processing. Just prior to stacking your data, we have a collection of traces going from near offsets to mid offsets to far offsets, all representing about the same geologic subsurface area. Okay? That's going to be our reference gather. Okay? From that CDP gather, we will compare it to our different models. And each model will predict a certain offset distribution for each bin in that model. Again, from bin to bin, there's a fair bit of variation in the offset distributions. Okay? So we'll take the offset distribution for a particular bin, we'll compare it to our super gather, and we'll say, well, in this bin, I won't get all of those offsets from near to far. What I will get is just that subset of these traces will contribute to a stacked trace in this bin. So we take the offset model for a bin, use it to define which traces from the super gather would contribute in that survey. We'll form a stacked trace from that subset and put it into this bin. And we go to the next bin, and we do the same thing. And you'll notice as you go from one bin to the next, the subset of traces we use changes. We're going to use the same reference gather to simulate an entire survey. So there's one thing that won't change in our simulated data. The geology won't change. We're going to use the same reference gather, the same geology to simulate every bin. What we will be simulating is the combined effect of changes with offset, changes of signal and noise. So again, if you take a look at even a strong reflector from near offset to far offset, that's changing. And if you had a survey that delivered only these offsets, you would get a different character stack versus a survey that delivered only those offsets, or a survey that delivered a complete set of offsets. So that's what we're modeling, is how sensitive is our model to imaging the noise, if you want, okay? Or the noise in the presence of signal changes. Okay, so what does one of these look like? Well, in this area, for the client that I've been describing so far, we usually take a couple of different CDP gathers, one that represents typically good data, one maybe that is a poorer data. We like to use 3, because I'm a Clint Eastwood fan. We like to simulate the good, the bad, and the ugly. Okay? I didn't mean to look at you, Ken, when I said ugly. That was coincidental. We like to take these 3 different references and just see how our simulations will vary with the typical rate of change of data quality. So in this area, this was a typically good area. This over here gave a little bit worse data quality. And to be fair, in this example, the client was fortunate. He had all pretty good data. Okay, it really never got really bad. But this, using his good data, we're able to simulate a 3D stacked section. You'll notice it's got no geologic change. There are some trace-to-trace variations, and that's just due to the different subsets of offsets that contribute to each trace. This is what he would get if he spent a lot of money and did a very dense survey. And I'll show you I'll show you 5 models going from the very good, which I'll call number 1, to the very sparse, which I'll call number 5. That's number 1, 2, 3, 4, and 5. And again, remember that this is his prime zone of interest, but he's also interested in imaging faults up through this area a little shallower. So as you go from the sparse, number 5, backwards to the good, number 4, 3, 2, 1, you can see that if he spent a lot more money, he could get slightly more interpretable data. If he goes sparser, he will sacrifice some of that, but save some money. On the good data area, it probably doesn't matter too much which way you go, and it'd be foolish to spend a lot more money if all your data was good. But let's do a simulation in the poorer data area. Okay, so using the poorer data, this is what his dense grid would give, his number 1 grid. There's his number 2, number 3, number 4, number 5. So that's getting pretty noisy. Not at his prime zone of interest, that's still interpretable, but this stuff up here is getting less reliable. And in fact, the data he currently was using in his first survey was this model. And what we did in this particular case was we were able to convince him if he went 1 notch tighter grid, he might get better data. And we actually made that affordable for him by changing his dynamite charge size and charge depth. And we were able to convince him to get a little better data. But again, it's a little bit hard to quantify from this graph exactly what we're looking at, how much are these different models changing the quality of the result. So what we do is we take all of the traces in a 3D volume and we plot them over his window of interest. So we don't get one set of traces, we get several thousand traces on top of each other, and the variation you're seeing in the amplitudes or the phase, that's the instability of the model. So this is our most stable model, the very dense one. As we go sparser, you can see that the instability increases. Okay? And that's a fairly easy thing to measure. We can measure the standard deviation of these amplitudes. So for each sample along a trace, I can measure the standard deviation relative to the average, to the mean. And we plot that, and we see through his zone of interest, extending from the yellow down to this, whatever color that is, marker, we can see his very dense model has some value. It's got a lower standard deviation and greater reliability. His very sparse model, a little less reliability. He was using the middle model, and what we're able to demonstrate here is by just going 1 notch tighter, he actually gets a significant gain in instability of his model. So we're starting to quantify these models a bit more. This is in his poor data area. This is where it really makes a difference, is notice the increase in instability as we go from the very tight model to the second, third, fourth, and fifth options. And we see a very large difference in standard deviation in there. So I just quickly want to take you through 2 other examples to show you the value of this tool in some other settings. Perhaps one of the most remarkable was in Argentina. And in this area, the client had shot several 3Ds. Some of the data, very good, very useful for his deep targets. Some of the data, a total washout. And the reason for this was some basaltic sills up in the very shallow, in the top 500 meters. Okay, now these sills, a lot of people think that, okay, the basalt just acts as a strong reflector and prevents your energy from penetrating to your deep targets. In fact, it's a little worse than that. Okay, And again, I suspect these animations won't work, unfortunately, but we can animate what a shot would look like, or we can model what a shot would look like in this area with no basaltic sills, and we can model what one would look like over here with the basaltic sills. And notice that these are not a continuous sill. There are various sills of different thicknesses, different lateral extents, and each little segment has a boundary, which acts as a scattering point to seismic energy. Makes high amplitude. This one works. Okay, so in the nice clean area, we propagate a wave field, we do generate a deep reflection. This guy's coming up complete with diffractions and reflections. And that will survive to the surface where our geophones will measure that signal. Relatively little noise. Okay, we're not going to be bothered by noise in that case. When we look at the same thing over where the basalt is got all these little truncations, every little truncation creates scattered surface energy, high amplitudes. And our deep reflections passing through that end up being dominated by the scattered surface waves. And we lose the reflections. That's what's happening in this poor data area. That's a snapshot of the high amplitude noise, and the very low amplitude reflection will just not survive compared to that strong scattered noise. So in his area, we could again pick out what does a super gather look like in his good data area, what does it look like in the bad data area, and what would the data simulation look like using his 3D model that he acquired. And it predicts exactly what we saw, where we have the good CDP gathers, we get good reflections. Where we have the poor CDP gathers, we get useless data. So what does he need to do the next time he shoots in this area? We investigated 3 different grids for him. We investigated the grid that he was using. We investigated one that would cost about 40% more. And we investigated one that would cost about 2.3 times as much. So if you think of $1 million versus 1.4 versus $2.3 million, it's not worth it for him to spend $2.3 million to get this data compared to that data. That's pretty interpretable. This is better, but it's not worth $2.3 million. Okay? So where his data is good, we don't recommend he changes anything. In fact, he could go sparser. But what he needs to do is solve what is he going to do in that bad data area. If he spends more money, will he still get the same bad data? Or is it possible he might get improved data? And we're able to demonstrate here that that's exactly what he's getting in the bad data area right now. And if he does spend more money, he may be able to find oil and gas in those no data areas below the basalts. This is something he can take to his manager and say, please, please, please give me $2.3 million. The manager might believe him. One last example from Colombia, a similar example in a good data area. This is in the foothills of the Andes, going up into the disturbed belt. In the good data area, using an original client's model, the original parameters, he was getting pretty useful data. He was considering doing a second survey over top and integrating the 2 surveys, and that's what he would have gotten. We recommended a totally new set of parameters that was going to be considerably more expensive. And it's not worth it. In the good data area, you don't see a significant change from the good to the bad. But you move now into the disturbed area where he was drilling dry holes, $15 million dry holes, each hole. Could we get him more useful data in that area? So in the disturbed area, if he stuck with his original parameters, he was getting pretty uncertain information in his zone of interest. By going to a new set of parameters, we can demonstrate to him he will get considerably better data, and maybe it's worthwhile spending the money. Okay? So basically this is a paper. It's not about your first program. In your first program, you have to design for the signal that you think you understand, and you're going to have to guess at what your noise conditions are. That comes maybe from a bit of experience. In your next programs, you can use the results from your first program to start to predict how to change your program. Do you need to spend more money or not? And if you're going to spend more money, will you get some value for it? Okay. Thank you for your patience and not pulling out the hook when I ran 5 minutes over.
We've probably got time for one or 2 questions. Peter?
Could you use parameters regular 2D survey to look at your data quality and predict what might happen in 3D?
Yeah, definitely. When we started developing this tool, for the most part, we were using the results from 2D data to run the simulations predicting the 3D. So having some seismic data is necessary. It doesn't have to be a 3D. The simulations work better off of 3D data, but definitely 2D is worthwhile running simulations on it.
Okay.
Is it possible to design your second survey and use the data from the previous survey?
Yes, that's what the client wanted to do in this one example here. He wanted to use the original data. He wanted to use his original survey and then just shoot another sparse survey kind of interleaved with that and then integrate them. And the problem is when you shoot a brand new survey that's dense, every shot is seeing a lot more receivers. When you integrate the two, each shot is just seeing a small subset of the receivers and vice versa when you go back to the source domain. So an interleaved survey is one way that chintz out a little bit, but it's not our recommended way. You only get about half of the statistics you get by reshooting with a new survey.
Doug?
Yeah, I was just wondering, are you doing NMO corrections on all of these traces that you're showing here?
Yeah. When we do the simulation, what we're trying to use is a super gather that already has basically a full set of statics, maybe not super fine-tuned residual statics, but it'll have all your statics, it'll have your NMO correction, it'll have a decon, but we try not to use anything that has a lot of heavy noise suppression, because one of the things we're trying to model is the effect of noise versus the density of your grid. So no, we're using something that's processed up to a preliminary stack just prior to stack.
Well, thank you again, Norm.
Okay, thank you.
Next speaker.
Thank you.